again for the kind introduction. So, to the organizers, really an excellent conference here. It's an honor to be here and have one of the plenary talks. Matteo, thanks a lot for introduction of all these microstructures. I will add some mechanical properties right now. So, as is already said, I will talk about anisotropy and damage tolerance. So, we will be looking at structural integrity right now. First of all, where is Kassel? So maybe not everyone here in the room knows where Kassel is. It's in the heart of Germany. So now we are here at Munich, and it's about 3 hours by train, and you're in Kassel. So it's always good to have a visit there, stop there by train, and have a look at this nice institute. So this is the Institute of Materials Engineering. Of course, Kassel is known for a lot of other things, so arts, for example. But we have really a lot of activities in materials engineering. Just to show a snapshot out of our labs. So in principle, we are looking at process microstructure property damage relationships. And in terms of additive manufacturing, we start with the printing. We will see the machines later on. Then we will have a look on microstructures by using SEM-TEM. We look quite a lot on residual stresses using X-ray diffraction. Then this is added by computed tomography, and all the things we build up here, at the end we destroy them by looking at the mechanical properties and especially by looking at fatigue properties. In future this will be added to the system, so it's in installation right now. This will be kind of unique in the world. It's a DED system we obtained using up to 7 different powders, wires as well, and we equip this with a liquid metal X-ray source, having a quite nice beam profile, as is highlighted here by the red curve. So in comparison to some older synchrotrons, we meet almost the properties of the synchrotron of 2nd generation. We will have a fast flat panel detector, so in principle on a lower level, but in principle we will be able to do the same things that are done nowadays in the synchrotron sources, and this is meant for materials development, so we only will print thin walls, not complex structures, but the purpose is to build up material libraries at that point. So come to Kassel in 2023, then you will see this in action. So before now, the results from the last years. At the end there will be a list of many contributors, and we will see who contributed to the whole story. We all know additive manufacturing is quite complex. So we have a lot of influencing parameters, and as Matteo already said, geometry and microstructure are established at the same time, and so it's hard to maintain the microstructures built in the blocks in complex structures. So the question is, how can we separate and control all these factors? There's another question that partly already has been answered by Matteo. What kind of unique microstructures can appear, can be promoted by the process venues we have to be used? And another question, and this is the right conference here to be asked this question: can alloys be tailored to meet certain demands and challenges in AM? I think we always have to look on these correlations I already mentioned before, so we have to link the process with the damage evolution at the end. So this is the chain you have to look at to bring this into application. And some of the challenges, at least my perspective in AM, and they are still open. So we have, of course, pores. We always will have pores, at least the small pores. We have rough surfaces, residual stresses, and this in combination with some critical alloys. We will have a lot of cracks being formed in AM, and we have very fast precipitation. We are able to control somehow the microstructure, but if the part is complex in its geometry, this may be a real challenge at that point. And this brings me to my agenda today. So I will talk about 2 different alloys. First of all, titanium alloys, well known of course in the community, so it will be Ti64 at that point. We will have a short look on post-treatment, and then there will be a second chapter focusing on steels. So different steels, 316L will be part of that story as well. The machines I have in my labs, two different ones on the right-hand side, an Arcam EBM system, so a hot bed process, and this run and enabled by the electron beam being used here as a heat source. To the left-hand side, a machine from SLM Solutions in Germany, and this is equipped with two different lasers. So we have in the same machine a 400 watt laser with a Gaussian profile and a top hat laser with a kilowatt maximum power that can be just switched during processing. And this is a degree of freedom not many machines have at that point. We have the platform heating up to 800 degrees C, so Julia Richter yesterday already showed we built quite a lot of structures at those very high temperatures. It's not exactly 800, so we go up to 780 degrees C. So looking at the titanium alloys first, so this is quite old part of the story. So this now focuses on processing of virgin gas atomized powder, and we look at machined specimens. So this is all machined material. I just want to highlight some very important aspects, especially when comparing those two processes. We have, when we look at the EBM process, hardly any residual stresses due to the nature of the process, the hot bed. If we look at laser beam powder bed fusion, so the SLM process, we obtain in certain depths of the specimens very, very high tensile stresses. So to bring those in application, we need to do at least a stress relief heat treatment. And this we did in this study. So we compared different Ti-6-4 alloys processed by electron beam powder bed melting and by the SLM process. The SLM material always was stress relieved, and we added the well-known hot isostatic depressing to get rid of the pores. Not really get rid, but to decrease them in size to a minimum level so that they're not detrimental anymore. So we have fracture surfaces at that point. So on the upper part of the side, a specimen that has not been hit, and we see a classical fisheye, so we can already see this is very high cycle fatigue we are looking at. And the fisheye fracture, in the eye, we see the initiation point, so of course this was a lack of fusion defect at that point. If we do the hip, the pores are under critical in size, so the cracks are started in the interior as well, of course, but at different features. We will see this in high resolution in a few seconds. This is just some snapshots on the fracture surfaces comparing EBM and SLM. In principle, we see the same defects, lack of fusion and those round pores. As we in principle use the same powders, only different in size, of course, but the nature of all those defects is very similar. And looking at the performance in the very high cycle fatigue regime, we see if we now consider those specimens that have not been hit, then they fall all into one category. So this is EBM as built material as well as the stress relieved SLM material. So this is in principle almost on one line. So this is a group of material that is then really hardly or heavily affected by those pores we see here, by the different ones, and of course most detrimental, the lack of fusion pores at that point. If we do the hip, as I said before, we will have those pores of minor size only, so much smaller at that point, and different features now come into play. And this is alpha platelets, well known for the Ti-6-4 system, being inclined by about 45 degrees to the loading direction, and those now start the cracks. As the mechanism is different, we come up here in the Wöhler type SN curve, so that we have much better fatigue properties after hot isostatic pressing in the Ti-6-4. I'm looking at a reference system at that point, so this is conventionally processed material. This is just taking data points out of the literature, so from colleagues in Kaiserslautern, and we see if we do additive manufacturing plus additional HIP, we almost can meet the properties of the conventionally processed materials. some recent literature already showed we can even be better if we decrease the temperature of the HIP cycle. So this was a standard HIP cycle at 920 degrees C we employed here. If you go down with the temperature and go up with the pressure, the properties will even be better than in conventionally processed alloys. So there is no more open questions. I think in that field the fatigue properties are very good. Now we asked ourselves what happens if we don't use the perfect powders. The whole community always tells we need to use perfect powders. But what happens if we now add some non-spherical recycled material? So what have we done? We now focus on the EBM process. And in the EBM process we have sometimes heavily sintered material. We have support structures. We can see just the arrangement in such kind of structures we considered here in those computed tomography scans, and those now we use to break them up mechanically. So this has then been processed mainly by milling processes, and the product you can see it to the lower right. So this is mechanically processed Ti6-4 stemming from sintered material. We see some bright features here, and the question arose, what is the nature of those features? So we looked into details, going again to computed tomography, and we can just see that the powder in its shape looks quite good. So some SEM images added as well, but we see those ill-defined particles. And looking at the density at that point of those particles, this is iron. This is introduced from the milling process itself. So we have 0.4% of iron included now in the material. So what have we done? We mixed these powders to the virgin powder and used different ratios of mixing. So 25% level, 75% level, not 100%. And then we printed this by using the EBM system. We have a reference image here shown to the top. We see some pores, of course. We see the traditional microstructure well known for EBM process Ti6-4. And to the lower part of the slide, we see porosity increases, at least when we have this fairly high amount of recycled powder. And we see that the phases change. So we have a higher phase fraction of the beta phase. This is, of course, related to the iron we introduced at that point. But in principle, still we can process this and we obtain solid material. Then we looked at monotonic tensile properties, and as expected, looking to the blue curve, if we add this 75% of recycled powder, we have fairly high strength, but ductility is very poor. So the reference curve is the green one. Surprisingly, the yellow one shows superior properties. So we see when we mix 25% of the recycled powder, we have higher strength and really good ductility maintained. So this is quite positive what we see here, but of course we want to go further, so we did fatigue. So we went to a fatigue study, and we can see some of the fatigue curves we obtained here. And looking at those fatigue curves, again we can see that this recycled 25%, so the mixture 75% virgin powder plus 25% of the recycled one, still shows reasonably good properties. So this is very optimistic in terms of this can be transferred to other fatigue regimes as well. So of course this here now is strain control testing, but currently some further experiments are running, so we are looking at the other fatigue regimes as well. So far no results at that point. But the things we already obtained, so this is of course not really statistically supported by a high number of tests, but we see, plotting this as Euler curves, all the results we have so far, that we again have similar properties for the reference material, so only virgin powder, and the one with the additionally recycled part of 25. If we go to the higher amount, 75% of recycled powder, of course we lose performance in the fatigue regimes we considered so far. Looking at fracture surface, to end the story here up, we see that the iron is homogeneously distributed. So it's alloyed when we do the processing, so that the iron flakes we had before are not present as flakes anymore. They are alloyed to the titanium system, and that explains all the things we saw before it. Good, this was the story about Ti64, and now we want to look at the steels. And again, I start with the standard gas atomized virgin powder, and looking at microstructures. We already saw a lot of nice microstructures before in Matteo's talk, and here we see that we are able to tailor microstructure by using this machine as well. So a columnar grain microstructure, fine grain microstructure done in one build, and we transferred this to nickel as well, and using this machine and the kilowatt laser at that point, we are really able to print single crystals. So a single crystal made of Inconel 718, 8 of 26 millimeter. I don't have an image today here with me, but this is published at that point. Looking at the influence of geometry, we see that when we use the same parameters, then we have different microstructures when we just decrease the diameter of a cylinder. So this is a simple cylinder, and we use the same parameters for printing the 316L, and going down with the diameter, we have a transition from equixed to columnar grained. And this columnar grain needs to be considered in all features of small size, because this then shows up. Most obvious in this specimen I show here. So this is two specimens where we imprinted notches of different shape, and the difference as well is in the size of the ligament. If the ligament is very small in size, we see there's a change in solidification, so that we have anisotropic properties here, a strong texture in that part that is characterized by low dimensions. The same holds true, as I showed before, now larger here on the slide, for those lattice structures, and we will see a whole session on lattice structures after my talk. Looking at bulk material, so this is the standard microstructures we see for 316L printed with many different parameters. We know, Matteo already showed this, we have submicron cells, they are very important for the properties. And in this case, if we do a hip cycle, so the right-hand side image, this is hipped at 1050 degrees C, 1000 bar for 2 hours. This is fully recrystallized at that point. And doing hip, of course, should improve the fatigue properties. Here in the 316L, it does in part, only to the right-hand side of the Euler type SN curve. We see we have improved properties, so the green dots here, this is the hip material, but if it comes to higher stresses, we have the superior answer for the as-built and only stress relief heat-treated material due to the higher strength. Because recrystallization just erases all the information we had before, so including those subcells, we lose performance, we lose strength. So in terms of fatigue, it should be considered if HIP is the right thing to be done using 316L at least. This should be avoided as well when it comes to graded structures. So I was fascinated about microstructurally graded structures as well. So we printed this block 316L. So this was done in, I think, 2013. And we used this dual laser SLM system and just switched the laser. So the embedded islands here, this is printed with the kilowatt laser and the surrounding with the 400 watt laser. And we can switch between fine-grained and columnar-grained material, and looking at the mechanical response, we can see that, of course, the coarse-grained parts have lower strength, and so we see much more deformation if we do a tensile test. So this is nothing but results obtained by digital image correlation at that point. So we can realize those functionally graded structures. This can be read out by eddy current technique, non-destructive, so we can imprint code in a part beneath the surface and read this out with eddy current, as I said before. So some ongoing work in that direction we do with a partner in Hanover. Very interesting now when it comes to the properties of those graded structures. So this is fracture mechanics in this crack growth, and I just want to introduce this type 5 sample here. We have the columnar grain material shown by the stripe pattern, fine grain is a white, and the test was controlled in a way that we should have a steady increase of this line. But we can see that this line here shows a flattening, and it shows that we have crack arrest. So by imprinting those elongated structures into a component, we can arrest cracks. And this, of course, opens up a lot of possibilities in design of safe, reliable components, so components that are able to hinder a crack in further growth. And for this, only the arrangement of the pattern has to be adapted to the loading condition and the expected crack path. We can deflect cracks, so everything is possible by just imprinting those structures at that point. This is one part of the story. Now I will switch over to different materials. This again is 316L, taken from literature. We see those columnar grains known before, so we never printed 316L on our EBM16. So this is the reason why we took this as a reference. And we worked quite a lot on different trip steels, and looking at these steels, we can see that we are able to control the appearance of the microstructure. So this is fine-grained isotropic material. This is a single wall, a thin wall, single layer, and we see we have those columnar features to the top, but when it comes to further heat input at that point, we have multiple phase transformations, and those phase transformations refine the microstructure. This is still fully austenitic, as is shown here in the EBSD image. Christian already showed at the beginning of the conference that we're even able to control manganese fraction at that point. We are able to evaporate the manganese by just setting the energy density in volume. And we see here for one of the data sets we have, this is a linear trend, so this can be controlled to a high level. And if we do so, we just can switch between the mechanisms. By evaporating the manganese in a steel showing twinning or transformation plasticity, then by just losing the manganese, the trip effect is supported, and so we have a different response in the material system. So we see this here in case of the hardening curve, so much more pronounced hardening. This is just due to the loss of manganese intended by setting the appropriate window in terms of energy density. This can be done in a graded fashion as well. So we build up graded specimens where we just embedded one part here, we processed with different properties, and we can see here to the lower right that we have a loss of manganese in the section that has been processed by a different energy density. So again, we can tailor not only the microstructure, but here we can tailor the composition to a spot and use this to switch in between different mechanisms. So it's not a functional material, it's a structural material, but the idea is the same. Anyhow, as you can see here, if we do so, the microstructure changes as well. And so far we are not able to separate all of it. So we are able to tailor chemistry, we are able to tailor the microstructure, but this is interlinked, and so far we are not able to really separate the control in that way that we have full control of a microstructure at a given manganese content. So coming back to the grain refinement, of course the phase diagram is very important, and the shape here of the phase diagram shows the top. So here we have those multiple phase transformations, and in principle, so the word intrinsic heat treatment has been mentioned quite often during the conference. We employ intrinsic heat treatment to refine the microstructure. And this is a material that is able to show twinning and transformation in its plasticity. We have very high damage tolerance due to those mechanisms. We see a microstructure, fracture surfaces here that are really not good at that point. So we see a lot of defect at that point. And looking at those defects that should show really poor properties, but compared to powder metallurgical raw, that is a reference here at that point, the properties of the material are almost as good as. So, looking at X-ray diffraction, of course, we were able to show what phases are present, and most obvious here from the EVSD micrograph, we see transformation-induced plasticity, so the trip effect in this, of course, is the key to really tailor damage tolerance in this system. And again, we see a sample here that has been fatigued thereafter, very poor in terms of porosity, so really huge pores at that point, but still relatively good fatigue properties. So just to mention a final story in this regard, as we did in titanium, we did now in steels, but this time this is pure iron, so harmful iron. We looked at in two different conditions, gas atomized versus water atomized. So in principle, many people are interested in water atomized powder, as this is much cheaper, but the morphology looks quite bad, of course. Flowability so is not that good, but still we tried. We tried to use this in selective laser melting. We see we even used relatively large particles at that point. So the fraction of particles we used went up to 100 microns, and in principle, normally for our machine, we only should use particles up to 60 microns. After that, we went to computed tomography to see what is the size and the density of the defects. And obviously, the water atomized powder is characterized by a larger defect density, but still looks quite good. And we have the number shown to the top, relative density of 99.97. So reasonable in terms of density. Looking at the microstructures, both look quite the same. So we have very similar microstructures in both cases, and the stress-strain response is similar. So we have a yield phenomenon, and this can be then explained by the chemical composition. So the water atomized was slightly different, and the chromium content here is the key to explain what happened there. If interstitials are able to move still in the microstructure, or if carbides and nitrides are then evolving. Again, looking at fatigue, in my opinion, it's always good to have a look at fatigue, because fatigue clearly shows if the material is good or not. And in this case, again, the fatigue properties are very similar. So we see curves, so we cannot explain this part here, but the rest of the curves is quite similar, and so we still see good fatigue properties. Looking at the half-life hysteresis loops, they are almost the same, so we would not be able to distinguish between those two different powders looking at those hysteresis curves. Looking at Wöhler type curves now plotted versus the strain value at that point, again, a reasonable fit of both conditions. So from these data, we just derived the conclusion that water atomized powder can be used even if this will be used then afterwards in a condition or in an environment where cyclic loading plays a role. And so, in my opinion, this opens up the opportunity to use different powders even. So a lot of these results I've never expected. But looking at fatigue, reasonably good. Performance level is not 100% anymore, but if we are able to design components, or if we are able to use a component that only has a reference level of 90% performance, we should look at these alternatives as well to broaden the impact of additive, and this of course always helps to decrease the price at least of the powders. And with this, I'm coming already to the And we saw that we looked at different things. I could tell a lot more, but I had to condense this to read the 30 minutes. I'm almost staying in the 30 minutes to keep here on track. The conclusions I already said before. So we should be open-minded in looking at different options, using different powders, and challenges still are open, of course, but tuning microstructures will help to have damage-tolerant alloys, and so there is a lot of things that are really helpful to tailor and optimize those materials. All the things I showed are taken from these references. As I said, this was not my own work, of course, so this is the work of my group in Kassel, so this is all the PhD students being active so far and the technicians. This is joint work with partners, national and international. I just summarized some of them here on the slide. And of course, thanks for funding to the funding organizations from DFG to AIF to Löwe. This is some specific organization to fund projects in the state of Hesse. So thanks for the presence here, and now I'm looking forward to receive the questions.
Thank you very much, Thomas.